Thank you everyone for being here. Thank you for the organisers for shifting the programme a bit so more people could be here. Apologies to the one group who I left standing for the software demo. I got a bit confused by the schedule. I will be available after the session if you do want to see the software then, or I can send you my backup slide pack if there were specific things you wanted to see. So I want to make the case for big data petrography, and this comes from my background of being a reservoir quality analyst in BP. I did a lot of studies where at the end of the work I wasn't really able to predict the properties I was interested in. So if you want to understand what controls porosity on a sandstone, that's a multivariate big data system. It's as complicated as the weather or as modeling galaxies in space. You need the kind of data in order to do that work. You need really big data. And so I want to make a case for doing this kind of big data petrography. And I hope you in your workflows think about how we can do petrography differently. So the aim of my little company, Rocktype, is to bring in an industrialization of how we do petrography. And when I say petrography, I mean the study of rocks, not just optical petrography. And in order to do that, we need automated data collection, and we need data-driven automated data analysis. So as I was hinting at, rocks are complex systems. If we're trying to predict porosity, permeability, compressibility, brittleness, the characteristics that these properties respond to are based on tens or hundreds of variables. And some of them we know, I've written a list. The provenance will affect the rock properties, climate, deposition, diagenesis, the different mineral phases and how they react with temperature, pressure, time, fluids, the texture, any bioturbation, any lamination, and the burial history. So all of this has to be integrated under the curve. This is a problem that is not actually possible for a human looking at a limited data set to solve. Experimental design tells us that in order to predict the properties of systems that have 100 variables, you need thousands or tens of thousands of samples. We need big N, big sample sets, in order to see the signal in the noise. So this is a cartoon graph I made just to illustrate that. So if this is a line above which you have a sample set big enough appropriately to answer these questions, I would say that the current studies we do now are down here. Now the x-axis is the dimensions, the number of variables we look at. So sometimes we do optical petrography, sometimes we do XRD, sometimes we do XRF, sometimes we do core analysis. Usually we do all of those things together. We spend a lot of money, a lot of time. We pull in a lot of expertise. And then we sew these data sets together that don't naturally fit together. And I think we learn, but we really never kind of knock it out of the park. Say, I know what controls the flow behavior in this reservoir. I can predict the properties of the next well I'm going to drill. So these studies are all underpowered. Having 100 samples, 20 samples is really not enough. So we should be looking, I would say, at industrial size studies. So if you have a well and you have fine-grained, coarse-grained, medium-grained, cross-bedded, laminar-bedded, all of these things, all of these units need to be sampled many times in order to compare apples and apples, so holding variables constant in order to look at the behavior of other variables. And I'm suggesting now that we should start looking at huge data sets for our questions. Thousands of samples, tens of thousands, hundreds of thousands, millions of samples. And at some point, hopefully quickly, we'll start understanding what is necessary, and we'll be able to bring the sample size down and the number of dimensions down. We won't necessarily need to look at all mineral phases, all flow phases. We won't need to look at all textural properties. We'll find the ones that are important for the work we're trying to do. So in order to industrialize our data collection, we need to be learning from manufacturing. So this is an example of how Magnum ice creams are dipped. And if someone was doing this manually, if you think of how someone might be preparing or loading or analyzing a thin section, say, they wouldn't be, this is many orders of magnitude faster. And this is coming into our industry. So this is a Testcam SEM auto sample loader, where you put 100 samples on a conveyor belt, you put a barcode under it, they go into the instrument does its work, and it spits that sample out the other side. So that's what I'm talking about when I'm talking about the industrialization of petrography. So looking at rocks, we're really just interrogating the electromagnetic spectrum. And the area of the electromagnetic spectrum we're interested in for rock properties lies between the infrared radiation range through the visible lights, UV lights, and onto X-ray and gamma rays. And I want to go through 3 types of industrial petrographic techniques that are starting to become more used in the industry. The first one had a poster up in the lower library a couple of days ago, and that's SpecCam by SpectraMap, and that's an infrared radiation technique. It's a camera, and it sits over a core, and you scan the core, and then you move that piece of core, that meter of core, and you put a new meter of core, and you can do this all day and all night and create some very big data sets. You have an infrared light source. You know the energy, you know the characteristics. It's shot to a sample, and the signal is returned to the camera. And that signal now has a spectrum which tells you something about the mineral phases present in that rock. It's a molecular technique, so it responds to bending of bonds and stretching of bonds. It's not an elemental technique. So it responds really well to things that have, for example, water or complex chemistries like clays, and also things like hydrocarbons. And it returns data sets like this from the SpectraMap people. So this is a well panel from a core, a few meters of core, and you have different fields here, different data fields, different mineral types, dolomite and illite, I see here, and some hydrocarbons. And importantly, this data set is continuous. So I am a massive fan of this technology. It's fast, it's non-destructive, it's quite cheap, and it provides data in a continuous format. So this is a printout from one of the deliverables, but in-house I use these data in their data format. For example, if I'm interested in understanding the presence of illite in a reservoir, in this example we see 6 meters of core, and I've shown the illite percent in those 6 meters of core. I've also taken those data and plotted them in depth. And I've colored anything above 6% illite red and anything below 6% illite green, because I see that the area of high illite corresponds to an oil-water contact. As a reservoir quality geologist, I'm curious whether the oil-water contact is there because of the illite, or if the illite is there because of the oil-water contact. And when choosing samples for another technique, for example, the SEM technique that I use, I want to choose my samples based on this kind of continuous data, such when I do my work, I can put those results, for example, porosity or pore size distribution or illite size, back onto this continuous data set, and then use that to upscale further to properties and data sets of interest. The next type of industrial petrographic kit I want to introduce you to is called Axial by Zeiss, and I've spent 15 years using optical microscopes to do petrographic reservoir quality, also heavy mineral studies. And this starts automating some of that work. So this is an optical microscope where you can put in 50 samples at a time. Again, they have a barcode on them, so you know which ones they are. And it goes and it looks at the sample in plane polar, in cross polar. It spins the sample. It also uses fluorescence. And it creates per sample a data set like this, which is in their browser package. Plane polar, and then images taken at set angles of spin, and in this case also fluorescence. It can also put in SEM data, EDS, mineralogical data, the type I presented in upstairs, can also be put in at the same time. And you can do that day and night and produce hundreds of samples of data very quickly. This is a candidate to use machine learning algorithms of image analysis to further learn about your rocks. So the technology that we have in-house that I use day to day is ChemScan, and that's a trademark by Thermo Fisher Scientific, and there are other competing brands out there which are also very good, for example, by Zeiss. And we have a portable instrument like this on wheels, and you can take core or cuttings or grains or fossils, and you cut them, you embed them in resin, and then you polish them to have a flattish surface. The flatter the surface, the more high-resolution scanning you can do with these. This is like optical petrography in that you point step across the sample, but whereas in optical petrography, you're maybe stepping a millimeter at a time. Here you're stepping at an operator chosen stepping interval of maybe 1 micron, 10 micron, 50 micron. And at each point, the electron beam interacts with the sample. It excites the electrons around the atoms. When they relax, an X-ray packet of energy is released, and the sum of those energies released are read by your mineral library in your automated instrument, and you use that to assign each pixel a mineral value. So I just want to show an example of how we do this work at increasingly larger scale. So I'm just going to present a little bit of data from a 1,000 sample study we did last year on the Barents Shelf. And we looked at 11 wells, and we looked at the chord intervals only in this case, and we were looking at it for log calibration purposes. Later, we want to do all the cuttings intervals. That's also possible with this technology, and we want to do all the wells. And I do speak to Eirik about ways that these things could go into machine learning, because ultimately, you would like to take data sets like porosity, pore size distribution, mineral phases, pore lining phases, and then link that in through the core analysis data, the log data, and the seismic. So you could also be looking at mineralogical cubes, things like that. So that's the kind of data sets we're aiming for. And I'll show you one of the wells from this study, which had a quarter of the samples. So this is one well from the Barents. I just wanted to illustrate that it was about half a day's work to collect these 250 samples. And it was 2 days of lab prep. So we've automated the lab prep. Our lab manager is from biotech industry, who doesn't think about taking one piece of rock and preparing it. She thinks about 1,000 pipettes. So, so we polish en masse, and we 3D print holders, and we do have a lot of secret sauce to make this go faster. And that's with one person. And with 2 or 3 people in the lab, we can prepare hundreds of samples in a day. It's about 2 day scan time, and I'll go through I'll show you what the data scan this quickly look like. And it's about half a day reporting, because we've set up a lot of the reporting workflows. And this is the kind of level we're working at now, and we want to go much, much faster. We want to go 10 or 100 times faster than this. We want to be creating huge data sets. So this is one well, and it's 11 cores from this well. And what we see is mineralogical data showing quartz-rich sandstones, porous at the top. We see units that are shalier, that have different feldspars coming in, and we see the carbonate units at the base. If we look at 3 wells together, we can make correlation patterns. And this is the kind of starting point that I use for doing reservoir quality studies and provenance studies. So this is bulk properties. This is just the feldspars. So you can use that to think about the stratigraphic units, to think about provenance. These are the clay species from that same run. So one run of one of these SEM EDS systems, you get a wide variety of data sets that different people can use at different parts of the workflow. So here we see illite and kaolinite and smectites and chlorites. And this is based on, I would say, about 600 samples generated in maybe 2.5 weeks. And these are the heavy mineral species from those wells. And there's a huge number of information below here that I haven't shown. So I show garnet, but of course we have 10 types of garnet. And I show tourmaline, but we have 10 types of tourmaline. So this is the starting point for doing very rapid heavy mineral analysis, very rapid provenance work, very rapid reservoir quality work, very rapid log calibration. You also, from this data, you calculate logs like gamma ray, density, neutron. This can also be done at well site in future. And also porosity data can be pulled out of this very quickly. So this is the data set underlying those graphs I showed. That was about 600 samples of 50 micron stepping interval ChemScan images. Now, the reason we like scanning at 50 micron is it's the fastest you can go in one of these instruments, because at this point, none of the time of your scan, which is about 5 to 10 minutes, is taken up in analysis. It's all taken up with the stage moving. So if you scanned at 100 micron or 500 micron, it would take the same amount of time. It also gives you a kind of view of the texture of the rock at this stepping interval. And the bulk properties, as I mentioned, if you scan at 50 micron, 10 micron, 1 micron, is still correct. And I see a lot of ChemScan work done at 10 micron, which looks very nice, but it's giving you much, much more data than you need. And it takes about 4 hours, 5 hours, rather than 5 or 10 minutes, because you still have 50 to 100,000 data points for your rock in that time. So compare that to 300 data points from optical petrography, and you've got a lot of information here. So these are two images, and I put images in this form because a lot of the conversations I have are that starts with the image with ChemScan. And the thinking is, wow, we have these ChemScan images, we can do image recognition and machine learning that way. But actually, we don't need to do that because these aren't actually images, they're data sets. They're highly labeled data sets that just happen to be recombined in a format that look like an image. But each of the 100,000 pixels in each of these images has itself about 200 data fields associated with it, all of which we can work with. So if you have 200 data fields, 100,000 points, 1,000 or 100,000 samples, you have a lot of data. And all of that has its associated metadata. So what is the temperature of the reservoir at that point, the pressure, the fluid type, the stratigraphic type. There's all the textual information that you also get from scanning. So a lot of information available. And this is that same data set seen over the 1,000 samples of this study. Now, I'm a proponent of data analysis rather than always data visualization, because as soon as we start looking at things one by one, we really limit ourselves. We screech to a halt. The computational power of a human is so much slower than the computational power of a computer. But it is fun, it is enriching to see the images, and it's good for QC. So we do still think a lot about how we can image these. So these are the 1,000 samples from that study. These are the samples split up in the 3 wells I just showed you. These are the samples of the first well I showed you, but split up in core number. So this is a kind of fun package called Zagami, where you can upload thousands of images easily. And if you upload a data table where you've been strict with the naming of the file and the naming of the row in Excel, then you have all of your metadata. So you can plot images by temperature, pressure, stratigraphic unit, well, anything that you have as a metadata fields you can. So that is quite fun. So the industrial approach that we're taking, I mentioned 10 minutes per sample, about 6 samples an hour. You can do about 120 samples per day. I'm being slightly bullish there because you're going 24 hours a day, so it's kind of well site standard. I'm being slightly conservative because I've taken out samples for sample exchange time and downtime. And the theoretical max you could do on a ChemScan per year, again, taking out some days for downtime, taking out some days for rerunning samples or making mistakes, you can do about 40,000 samples in a year with an instrument like the one we have in our lab. And if you buy a bank of them, you can do a lot of data. And right now, these instruments are quite expensive, but they are much better than they need to be. And I work a lot with the instrument manufacturers to say, can we be doing this work on desktop SEMs? Because SEMs have nanometer resolution. It's wonderful. But as soon as you start using EDS, which is creating your mineral maps, your lowest resolution is about 100 nanometers or about a micron. So really, you need the worst SEMs you can get. You need the kind of coffee machine size SEMs that the instrument makers don't like because they're not very good. But they're $10,000. And that's how research groups and individual workers can be having these instruments on their desktop, and they can be taken offshore. And some companies do have banks of SEMs like this. So, for example, Rio Tinto, a mining company, has about 10 of these at one site, and they have many more across the world. So some companies do create mineralogical data in a kind of industrial form. So in our company, the way we work to try to get there is using kind of Kaizen approach. This is a terrible word, but it's quite useful, unbottlenecking. It's kind of continuous improvement. So we're always looking at our process and seeing what is holding us back. So we got a ChemScan, we were scanning these 5-hour runs, creating beautiful data, realizing we didn't need to, that we could scan for 5 or 10 minutes and get the same bulk data. And it's better to scan 1,000 samples at 50 micron and then find out which samples are your mean and your outliers and so on in order to do high resolution scanning on those. And so, but then we weren't able to prepare in the lab enough samples to run these samples. So then we had to unbottleneck that part of our workflow. So we went from being able to prepare 10 samples in the lab a day to 1 to 200 samples in the lab a day. We planned this year to buy another instrument, so now we have to figure out how to go from 200 to 400 samples in the lab per day. We then realized that we had problems with reporting, and one of the main reasons there was the mineral list. So every time we ran a project, we looked at the samples, and we looked at the minerals, and we tweaked things a little bit, and we made it perfect. But as soon as you do that, you can only do one project a week. You can only do a few samples a week. So we made some automation decisions. And when I speak to other geologists about these automation decisions, there is discomfort. So we have a mineral list, which is here, 40 minerals. These are the ones we work with. They are fed through automated reporting for all the graphs, automated calculation of properties. And they're not always perfect. But for example, below this list of 40, there's a list of 130. And below that list of 130 is a list of about 500 minerals. So you can go and look at those. But those lists kind of need to be fixed. And they should only be revamped when you have done the R&D sufficient to say, OK, it's worth the pain of redoing all of our workflows in order to update this. So those decisions are a little bit tough for a geologist like me, a reservoir quality analyst who likes to look at the data. But as soon as we stop looking at the mineral lists, we could then go a lot faster. And having things automated means we're not nervous about bringing online another 2 or 3, 4 instruments because it should all operate in the same way. So we've talked a lot about experts and computers, and I think about this a lot, and I think about the workflows that we have. We frame the question, we design the study, we collect the samples and prepare them and analyze them. And we said we'll always still need experts, and I know that's true, but there are also a lot of fields where the experts are no longer human. And I think reservoir quality is certainly a field where the experts soon won't be human. And I'm apparently a reservoir quality expert. This is what I've done for my career. But I've only seen a few thousand, maybe a few hundred rocks manually. And my ChemScan in the last 3 years has seen many, many more rocks than I've ever seen. And in its lifetime, we'll see many more rocks than I would ever look at one by one. And these questions are data science questions, trying to pull out trends from big data sets. This really should be left to the instruments. I think if we did proper data science on some of these bigger data sets, the ability of the instruments to pull, the algorithms to pull out the controls on porosity, the controls on permeability, already well in advance of what we can do as humans. So I think we're already at a place here where the experts, I'm not the expert anymore, the algorithms are. And I'm happy with that. And I'm happy to let the algorithm and the machines do their work on each part of this. Maybe the algorithms should be designing the study. We discuss a little bit ad infinitum whether we should sample every meter, every half meter, or every rock type, or maybe we could start looking at some machine learning for answering that question. Collecting the samples. There's some well sites in the US where they've started putting automated mud logger collection boxes on top of the shakers. They automatically collect a sample, and you can set the rate, and then it winds it up into a big tape. It runs it under a UV lamp and under some gas sniffers. So you have a lot of automated data there already. And then, of course, data analysis, communication, I put in brackets because it depends about your reason for communication. Is that in order to make decisions, or maybe in some areas the machines should be making the decisions? I know there's some big companies out there that are trialing running AI boards alongside human boards to see who's making the better fund decisions. So we'll see where we get with that. So I'd like to thank a few companies, Agami, MPD in Norway, and Statoil. And I'd like to thank Zeiss for letting me use their images of their technology, and SpectraMap, and of Thermo Science, Fisher Scientific. And thank you all for listening. Thank you.